So where we left off here in lecture is we were in the idea of really conversion problems and excuse me, dimensional analysis. And remember, dimensional analysis is basically a way that we kind of work out problems, conversion problems specifically, where we use equalities. We figure out some conversion factors to use, which are just fractions. But the key to sort of dimensional analysis is really showing, as we talked about last time, sort of that unit to unit cancellation. So it's really important that when you do these problems, it's sort of one of the skills you're supposed to be learning is to how to sort of properly show dimensional analysis, that you do really sort of set up your problems this way where you can see the units canceling. Basically, we're multiplying across the top, dividing by the bottom. We also want to think about the sig figs like we talked about last time. You know, for the most part, if it's some type of conversion factor that does come from an equality, especially if it comes from metric to metric equality or English to English equality, or some type of exact crossover equality like 1 inch is 2.54 centimeters. We don't need to be concerned about the significant figures of those conversion factors, which again, in 90% of the time, 99% of the time, probably that first number is probably the right sort of significant figures your answer should have, as you're pretty much just doing multiplying and dividing, which means we look at sig figs and we're looking for the smallest number. Remember though, that if we do come across technically an equality that goes from English to metric, sort of crosses over, that's not an exact equality. We should kind of look at the significant figures in that sort of equality or conversion factor. Any questions on any of that stuff we talked about last time? All right, so I think we laid it up here. We didn't do this one, right? So why don't you take a minute or two here and see what you come up with. There's some equalities, and then we'll look at it here in just a sec. Okay, let's take a look at this. So remember that you want to find the right equalities. Really, as we talked about as well last time, that pretty much from any equality, you can write two conversion factors. So again, if we sort of wrote our conversion factors here for each of those, that's going to allow us to sort of get to where we need. We're clearly going to start with what was given to us, which in this case is 5 pints. So we have 5 pints. Remember that although it's not really written as a fraction, we can kind of think of it as, sort of being up on top. And remember that opposites basically cancel. So we want to put pints on the bottom here. So we would use obviously this one first. Put in our 2 pints here on the bottom, our 1 quart right up on top. If we stopped right at this point, basically the pints and the pints would cancel. We would be left with units of quarts, which is close to what we're looking for. You can, if you wanted to, get an answer at this point, or you can just continue on with the calculation. I'm personally just going to continue on with the calculation. Here, quarts are on top. We want to get rid of that. So we would go to our other set of conversion factors. Like that guy would work very well for us. So we would go with 1 quart on the bottom, 946 milliliters up on top. Again, the quarts here are going to cancel because we're essentially dividing them by each other. So they basically, we would be done. We are left with just milliliters. So we want to basically multiply everything that's up on top there. So that is 5 times 946. We're going to come back and divide by what's on the bottom there, which is 2. Gets us a number on our calculator of 2365, which would be milliliters in this case. We do want to look at significant figures here. So probably back here, since these really sort of exact numbers, that would have 2, which would take us to here. So we could round this to 2,400 milliliters, or if we wanted to, we could do a little scientific notation if we like. 1, 2, 3 milliliters would be our right answer here. Any questions on that one there? Now, also really important sometimes, or where sometimes people make a mistake, is sort of in the calculation part. They try to put too much in their calculator at once. So, they'll put all the numbers up on top, then they'll come back and try to put all the numbers, if there's a lot of numbers, on the bottom. And sometimes if you don't do that correctly with parentheses and all that on your calculator, you will get the wrong answer. So if you never want to sort of make an error, you can pretty much multiply as many numbers as you want up on top, hit equals, divide by the first number, hit equals, divide by the second number, hit equals, and so forth. And you'll always sort of get the right answer if you sort of put it in that way. I've seen many times if there's a lot of numbers on the bottom, people try to squish it all on their calculator at once without the right parentheses, and usually will end up with the wrong number. Any questions on that? All right, so let's try one more here. All right, so why don't you give this a try? You're stranded 125 miles away from home. You have no money. You decide, hey, it seems like a nice walk. Why not? You're going to walk an average of 55 feet per minute. How many days is it going to take you to get home? All right, so take a couple minutes, see what you come up with. Basically going 125 miles, which obviously is a length or a distance. We are moving at an average of 55 feet per minute, which is a rate. And a rate, right, is how far you go in a certain period of time. That is really what's going to allow us to go from sort of length to units of time, since we're looking for how many days, which is a unit of time. We do have a bit of a problem. We have miles in terms of one of the units, and we do have feet in terms of the other unit. So we do need to do a conversion sort of before we could use them together. And you really could do either conversion. I'm personally here, I'm going to take the miles and convert them to feet. So I'm going to do that first. So I'm going to go with 125 miles. Miles are on top. So using this equality here, we're going to go opposite and put miles on the bottom and 5,280 feet up on top. There, the miles will cancel. 660,000, I think. We end up with 660,000 feet, which are good because that is the units that we see here in basically our rate. So we can use that rate like a conversion factor. So basically we will take our 600 and maybe, I didn't try again. I'll just draw weird things, try that again. 660,000 feet. Using our rate as a conversion factor, we want the feet to cancel. So feet are going to go on the bottom here, and that's going to be 55 feet per minute. At this point, using that, that is what's really going to convert us out of length into time at this point. Again, you could, or you could continue on. Here, I'm going to continue on. I'm in units of minutes, which is close to what I want, but I need to get to days. So obviously, a few conversions. There are 60 minutes in an hour. Again, that would cancel out the minutes. And again, as we talked about last time, there are only 24 hours, right, in one day, not 60. So 24 hours in one day there will cancel out our units of hours. It leaves us with days, which is the very last unit that's left. Here, we're going to go and multiply all the way across the top. And then we're going to come back here and divide by what's on the bottom. And if you do that, we will end up with 8.33 days. A nice, if you don't stop, I suppose, you know, all that good stuff. Significant figure wise, really everything here had three significant figures, right? The 55.0 is three significant figures, and the 125 also three significant figures. So three seems like the one. Yeah, so you, I, yeah. So one of the skills you're supposed to be learning is basically what we have down here on the bottom. And this is basically what is referred to as dimensional analysis, setting it up like that. So they do want you obviously to learn that. And that's really how you should work out most problems that are sort of like this. And they do expect it as you continue on with chemistry to sort of work about that way. So you see the units and stuff like that. So you do need to kind of set it up like that. Now you don't necessarily have to do it all in one sort of run here. You can kind of do the first conversion, get an answer, do the next one, and do the next one, but you still need to kind of show the units and everything canceling out. A couple of reminders: if you do sort of get an answer sort of in between each step, try not to round to the very end like we talked about, and then kind of clean it up at the end. But you definitely do need to kind of show it like that. Yeah. Other questions? Now, in terms of for credit, do you need to show all this? The answer is not really. So, you know, if it helps you show it, you don't need to show that, but you do definitely need to show that setup along with obviously the answer and stuff like that on the bottom to receive full credit. So that questions on conversions, dimensional analysis, how they do it. Okay. It's a really badly written equal sign. Still getting used to writing on this screen, you know. Just cleaned up a little bit here, so but yeah, it's just equals. Other questions? Okay. All right, then let's talk about density here officially. We sort of talked about it the other day in lab, but let us get into, you know, sort of what density is. Density really can be defined as we talked about, the amount of matter there is present in a given volume of a substance. Different densities determines whether or not, you know, something will sink or float, for example. So as we sort of talked about, I think the other day there in lab, you know, in something like water, you know, if you have something that is more dense than water, we would expect it to sink. If we have something that is less dense than water, we would expect it to float. And also, as we talked about there in lab, you know, if you're thinking about sort of liquids as well, you know, if you put a bunch of liquids together, they also will, you know, separate themselves out in terms of their different densities, with the more dense obviously being towards the bottom, the least dense being up there, you know, towards the top. When we talk about water in sort of the sort of accepted value of the density of water, as we also talked about, pretty much, you know, if somebody says, hey, what is the density of liquid water? Most people will say it is 1 gram per milliliter is the accepted sort of value. As I think I mentioned during lab, density is a value that does change with temperature. So if the temperature sort of changes, so does the density value. But, you know, if you're doing a problem for the most part or something like that, and you need to use the value for the density of water, probably almost a safe bet just to use it as 1 gram per milliliter, unless it specifically says something about temperature, and then you should probably find, you know, the appropriate value for it. So there is a formula that goes with density, and the density of an object can be found by taking the mass divided by the volume. And again, that is something that you should know. Again, will not be provided for you. Typical units, and this should be, by the way, it just didn't come out very well here, but it should be grams per cubic centimeter. The cubic should be up there. Remember as well that a mil is the same, or basically a 1-to-1 conversion between them. And we talked about different ways you could get the volume. Obviously, like we did in the experiment the other day, you could just simply take a reading, which would obviously give you usually just the milliliters. If you have some type of solid object like our wooden blocks that we were using in those couple of experiments, you could do some measurements and take the length times the width times the height, and that will get you the volume. And also, as we talked about, this is a formula that you do need to be able to properly rearrange. So density is mass over volume, which means the volume is mass divided by density, and mass is volume times density. And again, I think I drew on the board in lab the DMV triangle that people like. So again, density is mass over volume. Volume is mass over density, and obviously mass is density times volume. Questions on that there? All right, so let's take a look at one here. A block has a volume of 25.3 cubic centimeters, has a mass of 21.7 grams, calculate the density. So obviously when we look at this one, we would look at the density formula, which is mass over volume. And in this case, we could identify what these things are. So obviously that is our mass, which is 21.7 grams. That right there, remember, is a volume when we have cubic centimeters, again, not a length. So our volume would be 25.3 cubic centimeters, which means really in this case, we have both that we need. So all we have to do basically is just plug it in there. And if we do, the density in this case would be 21.7 grams divided by 25.3 cubic centimeters. And in this case, that gets us 0.858. Now the units here do not cancel, so they do remain, and that is grams per cubic centimeter. The number always stays with the grams part, and it's always per 1 milliliter or cubic centimeter, basically. Here, significant figure wise, we're dividing. So we look at significant figures. So top number has 3, bottom number has 3. So we end up with 3 significant figures there on terms of the answer. Any questions on that one there? Now, we also talked about, a very, very common way, especially dealing with density of a solid object, that we try to determine basically the volume. So 3 ways, as we talked about. We can take a reading. We obviously can take some measurements like length measurement. The third way here is our volume by displacement. So as we talked about in lab, and as you part B of, you basically, if you fill a glass container with some water or some type of liquid, and you basically submerge some type of solid object, like this lady jumping into the water. Before we begin, we have an initial volume. When she goes into the swimming pool, I guess, the volume of the liquid will rise. And basically what she will do is a solid object will displace a volume that's equal to its own volume. So we end up with sort of a final volume over here. And that means that we could simply find the volume of an object by taking the final volume minus the initial volume when we do any type of volume by displacement. And it's a very, very common way, very easy way that you could kind of determine the volume of something that is solid. Just simply drop it in some liquid and figure out the volume that is displaced. Any questions on that there? All right, well, hopefully, these are not just markings, but also a ladder, so she could get out, I hope. All right. Otherwise, she'll be there until next semester, I suppose. All right. All right, so why don't you give one a go here, see what you come up with. So take a minute or two, see if it fills a graduated cylinder, 25 milliliters of a liquid, drops in there a solid, the volume rises to 33.9, and the solid had a mass of 63.5. What is the density of the object? Okay, let's take a look. So this is very much like what we did there in that part of the experiment. We basically got a graduated cylinder. It was originally filled up to 25 milliliters. We took this solid object, dropped it in there. Obviously, we're going to see the volume level rise, in this case to 33.9 milliliters, and the object obviously has a mass of 63.5 grams. So we can we can determine the volume by displacement here. So volume of our object would be our final volume, which was 33.9 milliliters, minus our initial, which was 25 milliliters. And if we do all that good math there, looks like 8.9 milliliters. That's good because now for our density, we have both the mass and the volume. So plugging that in, 63.5 grams divided by 8.9 milliliters. Again here, none of the units cancel, so they do remain. And we end up with a density of 7.1 grams per milliliter. Any questions on that calculation? Yes, sir. It is. So remember, we want to kind of keep track of what we're doing in terms of math. So really the first thing we did here was subtraction. So here we would be looking at decimal places, which is 1 decimal place, which means our answer should have 1 decimal place. Although it has 1 decimal place, this number has 2 significant figures. So when we do the very last part of the math, we're basically looking at significant figures because we're dividing. So we're taking basically 3 significant figures there up on top, divided by 2 significant figures. And that is how we end up with 2 significant figures there on the answer. So again, we do want to kind of keep track of significant figures and all that as you're doing the calculation. Round as you're doing different parts, but you should keep tracking of it and sort of carry over to like your last calculation. Okay, maybe I was looking at decimal places, but now it has this many sig figs. Now I'm looking at sig figs, and that's what my answer should be. Other questions? So here again is some density of some different objects. We have water, which obviously, as you can see here, is 1. By the way, water is a unique sort of property. When we think about the density of something like ice, it's actually less dense than liquid water, right? When we put our ice cubes in our drink, they end up on top, right? And water is a very unusual substance. Most substances are more dense in their solid state than their liquid state. Water is one of them. Because of the way they come together in sort of its solid state, it creates a lot of open space between the different water molecules, increases the volume. So what ends up happening is as the water molecules in the ice state come together and they bond, they got all this open area that creates a much larger volume. If you think about density, which is mass divided by volume, this number gets bigger, density gets smaller, and we actually see a smaller density for solid water, which is ice, obviously, than liquid water. Again, a very unusual sort of characteristic. Most substances, solid is more dense than liquid. Yes.
Water's density increase with increase in temperature then? Like obviously also
Yeah, so the density does fluctuate with the increase in temperature. The greatest density that we typically see is about 4 degrees Celsius, which is about 1 gram per milliliter. And the lower than that, it's something like ice is like 0.99 something like that, so it's a little bit less. All right, and then obviously there's just some densities there. All right, let's try one more example here before we wrap up density. Student needs 150 cubic centimeters of salt in an experiment. The density of salt is 2.16 grams per cubic centimeter. How many 1 pound boxes of salt do they need? In 1 pound, there is 453.6 grams, in case that helps. All right, so we're looking for how many 1 pound boxes do they need. So take a minute or two to see what you come up with. Student needs 150 cubic centimeters. Remember, that is a volume. We are given the density in this case, which is 2.16 grams per cubic centimeter. If you wanted to approach this like a dimensional analysis problem, you could actually use this like a conversion factor. You could use it like this. You could also flip it around if you wanted to sort of do a dimensional analysis problem and flip it like this. You obviously could also just obviously plug and chug into our density equation here. And since we do have obviously the density and the volume, it would definitely make sense to solve for the mass here. And the mass would be volume times density. So the mass would be our volume, which is 150 cubic centimeters. And again, here, I'll just kind of set it up a little bit like dimensional analysis. 2.16 grams up on top, cubic centimeters on the bottom. Here, the cubic centimeters will cancel each other out. Multiplying across 150 times 2.16 yields us 324 grams of salt on our calculator. If we were looking significant figure-wise, we are multiplying. That is 2, that is 3, which means we probably would round out to we need something like 320 grams of salt. We also always want to make sure as well that we do answer the question it's actually asking. In this case, it's actually asking not what the mass is, but how many 1 pound boxes would you need, right? So you would need 1 and you would have some left over, obviously, since 1 pound is 453. So you would need 1 box to spare. Any questions on any of that calculation there? Questions on density, how to calculate it? Obviously, again, you do need to know the density formula. You do need to know, obviously, how to properly rearrange it, be solved for density, volume, mass, any of those things. Any questions on that? Okay, I think that's going to wrap up chapter 2. There might be some notes on specific gravity. We're not going to worry about specific gravity, so you don't have to worry about it either. And we're going to roll on to here chapter 3, so you don't have to worry about anything that says specific gravity at that point. Just give me 1 sec to in chapter 3, not too long of a chapter here. We're going to talk about matter. We're going to talk about different states of matter. We'll talk about mixtures and elements, and not too much. So let's get into it. So matter, as we talked about, is anything that basically occupies space and has mass. And as we've talked about, or as you may know, there's really 3 states of matter. There is the solid state. And really, in most cases in the solid state, you really do have a lot of guys packed in there, pretty dense to one another, pretty tight to one another, not a lot of room for movement. We then have the liquid state, which we still have everybody fairly in there tight to each other, but there is a little bit more room for movement, which is why liquid, right? They're able to kind of move past each other. Liquids are fluid, and that's really why. And then in the third state of matter, there is gas, which basically everybody has at that point completely broken apart from one another. They're flying around, as we'll talk about when we get to the gas chapter. As they're hitting the container walls, they're causing pressure that we associate with gases. A couple important things as we transition from these different states. As we go from solid to liquid, that is the process known as melting. If we go from liquid back to solid, that is the process of freezing. If we go from liquid to gas, that is the process of evaporation or vaporization. If we go from gas back to liquid, which is a common thing, that is the process of condensation. There's also a process where we go from solid directly to gas, and we skip the whole liquid part of it, and that is what is known as sublimation. And as you might imagine, you could actually go from gas back to solid, skipping again the whole liquid part. And that is what is known as deposition. Not under normal conditions. You typically will get the liquid water, some liquid water in between. There is different things that you could do, like play with temperature pressures to make things like that occur. But under sort of normal conditions, obviously, it does not occur. You get the liquid mass. We do see under kind of normal conditions, something like dry ice, which is not water, it's carbon dioxide. If you ever use dry ice or seen dry ice, it goes directly from solid to gas, skip the whole liquid part. Also very, very cold. It will burn you if you touch it, right? Yeah, so, but you definitely don't want to touch dry ice, obviously. But it does skip that whole liquid part. Going the opposite way, actually, from gas to solid, skipping the liquid. You're maybe old enough still to remember things like DVDs and CDs. Yeah, they're like shiny on top. Google it if you don't remember. But you know, that's how they would deposit sort of metals on the top of those things as you go through it. Now, when we talk about melting and freezing, does it occur at the same temperature or different temperatures? It does actually occur at the same temperature. So both of these processes occur at the same temperature. For example, something like water, that's 0 degrees Celsius where that occurs. It just depends really at 0 degrees Celsius. You actually have both phases there at the same time, like ice crystals. Not until you get a little bit above 0 degrees Celsius, you got liquid water. Not until you get a little bit below 0 degrees Celsius, you have ice. And the same thing over here, evaporation and condensation also occurs at the same temperature. And something like water, 100 degrees Celsius, the normal boiling point water is where that occurs. And again, exactly at 100 degrees Celsius, at exactly 100 degrees Celsius, you got both of those transitions occurring. And it's not until you get a little bit above 100 degrees Celsius that you have gas, not until you get a little bit below 100 degrees Celsius that you have liquid water. Again, exactly at 100 degrees Celsius, you got kind of both things occurring. Now, it also basically involves energy when we talk about to liquid to gas. We need to put energy in to do that. Our energy is absorbed. And typically in processes where we put energy in or energy is absorbed, that is what is sometimes referred to as being endothermic. Opposite is true if we have gas molecules flying around. If you remove energy, release energy, they cannot fly around as fast. They come in contact with each other. They don't have enough energy to escape one another, and they kind of go into the liquid phase and then continue to take out energy. They really clump together because they have no more energy really to get by each other. And going the opposite way from gas to liquid to solid, energy is released. And that is what is known as exothermic. Any questions on any of those differences there? All right, so let's talk a little bit more about these sort of different states here. Maybe okay, there it is. Oops. So matter is basically anything that has mass and occupies space, which is pretty much everything. Solid things are, for example, things like wood, bone, steel. Solid things have a definite shape, and they're very difficult to change the shape of it. Sometimes referred to as being very rigid. So obviously like this board, very hard. You can't just kind of fold it over or anything like that. It's very rigid. Liquid, on the other hand, has a definite, does not have a definite shape, but does have a definite volume. So what that means is, for example, if you had 10 milliliters of water, and you put it into a water bottle, shape of the water bottle. If you took that 10 milliliters of water, put it into the trash can, it would take the shape of the trash can. Put it into one of those silly straws, obviously it would take the shape of the silly straw. A definite volume means that if you started with 10 milliliters of water and you didn't, if you're not a klutz and you didn't spill it, you should end up with 10 milliliters of water no matter where you transfer it to. But it will definitely take the shape of the container. Gas, on the other hand, takes the shape of the container. It fills it uniformly. The idea there is gas molecules are constantly flying around, which means that basically it will fill sort of the container uniformly. And we oftentimes, when we deal with gases, as we'll talk about when we get to that chapter, we oftentimes look at the volume of the container rather than the volume of the gas. And we assume that the volume of the container is the volume of the gas because it's constantly flying around basically and filling up the entire container. So as you can see here, the different shapes obviously liquid can take. Here, as we were talking about earlier, here's basically the three different states of water, our solid, liquid, and gas. And again, as you can see here in the ice state, as I was talking about, when those water molecules really do come together, we get all this open sort of areas here between the different water molecules that basically will lower the density of it. And again, why it's less dense. Then as you can see in this case, the liquid water molecules are actually able to kind of get closer to one another than they can in the solid state. The state of a given sample of matter depends on the strengths of the forces among the different particles. So what that means is the stronger the forces, the more rigid something would be. What that means is sort of the stronger the force that holds sort of one molecule together with another, they're going to allow those guys really to pack in pretty tight to one another, be in there pretty dense with one another, and it usually results in a stronger density. Something where we have a lot of sort of weaker force. You know, if this is much weaker, it's going to allow these guys really to kind of get away from each other a lot easier, and it can't go into, for example, the gas phase. That's, for example, as we'll also talk about in a later chapter, some things like organic molecules. They have very, very weak forces that hold them together. That's why a lot of organic molecules are very flammable and go into the vapor phase. The first several organic molecules are things like methane, propane, butane, which you may be familiar with. It's basically gases, right? We use them. You can light them on fire. Basically, they're very flammable. And that's really why, because they're held together by very weak sort of forces, allows them to really be in sort of the gas phase relatively easy. So let's talk a little bit about some properties of matter, physical and chemical properties. A physical property is something that can basically be measured by some type of observation. Typical physical type properties are things like odor, color, definitely the state of the matter, solid, liquid, or gas is something that is, you know, a very common sort of physical property. Density, melting, and boiling points. Physical properties typically go with physical changes, as we'll talk about, but basically in a physical change, what you start with and what you end up with are still fundamentally the exact same thing, maybe appear differently. So for example, ice and liquid water, they're both H2O. The only difference between them is their sort of physical appearance, if you will. But fundamentally, they're both H2O. So the transition when you take ice is actually just a physical change because you have not changed fundamentally, you know, what it is. So, you know, something is green, you know, something is blue. These are very common sort of physical properties which sort of go with those physical changes. Obviously here, as I mentioned, you know, we can take a block of ice, You can measure things like the melting point, the boiling point. And again, those are all just physical sort of properties that are occurring. Again, fundamentally, it is still H2O all the way through when you go from ice to basically liquid water. Both are H2O. So again, this is basically a physical change. And basically what you start with and end with is the same thing, basically. So it's basically the same fundamental thing. What you start and end with, definitely physical change. A chemical change, for example, or a chemical property is a little bit different than that. A chemical property is basically the ability of a substance to undergo some type of chemical change or chemical reaction, or its ability to resist some type of chemical reaction, basically. Chemical properties usually go with chemical changes, and chemical changes are different than physical changes. Chemical changes, what you start with and what you end up with, are two fundamentally different things. And the key there is you cannot do any type of physical sort of process to it to get back your original substance. So for example, in a physical change, when we're talking about the ice cube going to liquid water, you can simply take the liquid water, put it back in the freezer, right? And you have your ice cube back, right? You just freeze it. If you take something like water and you run an electrical current over it, you could break it up into hydrogen gas and oxygen gas, which, you know, you could freeze it, boil it, whatever you like to do with that. Not recommended probably, but you will not get your liquid water back in that particular case. Rust, for example, rust is basically iron metal plus some oxygen gas, and basically they come together through the magic of chemistry and form iron 3 oxide. Here, the iron and the oxygen have now basically bonded together. Again, you can put it in the freezer and all that. You're not going to get the iron metal back by itself. You're not going to get the oxygen gas by itself by any type of physical means. So typically a chemical change is referred to as a chemical reaction. And that's the important thing. What you start with, what you end with, two fundamentally different things. You have really changed it to something new, and you won't be able to, again, kind of retrieve the original guy from it. Any questions on that there? So this is the example I just mentioned. If you take, oops, go backwards. If you take, again, hydrogen gas and oxygen gas, they will form water, which is sort of the opposite one. Again, when you get water, you can heat it. You can do whatever you want to it. You will not get the hydrogen gas or oxygen gas back. That is a chemical change when we're going even in the opposite direction. Hydrogen gas plus some oxygen gas making water. Nothing's balanced here, but that is a chemical change. We know that by simply if you ever boiled water, right? You don't get hydrogen gas, you don't get oxygen gas by doing that. You get basically steam, which is still water as well. That's a physical change. It would be a bad news if that happened. You would never get to, you know, boiling your water for your pasta. That would not be good. Obviously, if we ate a hard-boiled egg or something like that, that is a chemical change that occurs. And obviously, when you eat food, enzymes and stuff like that, you know, obviously completely change a lot of what you digest into new things. So the key there between the two things, physical change, what you start with and what you end up with, fundamentally the exact same thing. Again, if you took a peanut and you crushed it, still a peanut, just crushed in a whole bunch of pieces. Chemical change, on the other hand, does change to something fundamentally new, and you cannot get it back by any type of physical means. And obviously we call chemical changes, typically chemical reactions. And as I wrote a couple of those sort of equations, that's usually how we represent chemical guys by equations here. That look something like this. And we'll talk obviously more about those guys later on. So let's talk a little about elements and compounds. An element is a substance that cannot be separated into any smaller parts by any type of chemical means. Elements, if you look up there on the periodic table, those are all elements. You could think of elements as really the basic building blocks of everything in chemistry. You're kind of like the alphabet, if you will. You know, in the alphabet, we got like 26 letters, I think, still-ish. And we can make a whole combinations, obviously, of those letters. Same idea with our elements, different combinations of the elements that come together. Different compounds, different sort of molecules, if you will. And we get different combinations. Most elements, as you see on the periodic table, are what are referred to as being monoatomic, which means they basically come as one atom. An atom is basically the simplest representation of an element. As we'll talk about in the next chapter, it has protons, electrons, and neutrons, but most things are monoatomic. There are certain elements that come as molecules. H2, O2, N2, and all the halogens is correct. F2, Br2, Cl2, and I2. These all come as twos. These are what are referred to as diatomic molecules. A molecule is basically a combination of two or more atoms together. So when we look at something like hydrogen, it is basically an atom of hydrogen bound to an atom of hydrogen. And because it is two hydrogen atoms together, it is considered a molecule, but it is still an element because both of those are hydrogen. They're the same element. So an element can be a molecule. So let's talk a little bit about a molecule here, which sometimes gives people trouble. Is basically the combination of two or more atoms. So H2, O2, N2, and so forth, they are all diatomic molecules, but they're all considered elements. So if you have the element of hydrogen all by itself, not combined with anything else, it comes as H2, as a diatomic molecule. Sometimes, yeah. Yeah, like iron metal would be just Fe by itself, iron, yeah. No, they would just, so something like, for example, iron, you know, would just come as basically, you know, one atom by itself, yeah. Now, sometimes people get molecules and this idea of a compound confused. Now, a compound is the combination of atoms of two or more elements together. So a compound has to be two or more elements that are together. And that is why if we look at something like water, which is H2O, that is a combination of hydrogen and oxygen. Now, that is two different elements, which means this guy here is a molecule because it is two or more atoms that are together. They just happen to be hydrogen and oxygen together. This guy right here is a compound because it is two different elements that are together, hydrogen and oxygen. But water is not an element because it is two different elements together. Something like H2 is an element because it only contains hydrogen. It is also a molecule because there's two of them together. It is not a compound because there is no other element there. So H2 is an element, a molecule, not a compound. Water, which is two elements together, is a compound and a molecule, but not an element. Any questions on sort of the difference? Yes. Yeah, so we'll get into that. Technically speaking, something like a aluminum oxide, if that's what we're talking about, some people will call it a molecule, but it's really an ionic compound. And it's the way it's held together is differently than something like water, which is sharing electrons, something like aluminum oxide. What's that? Pure metals by itself. Yeah, so if you have something just like, I'm sorry, maybe I misunderstood. Just something like aluminum by itself, is that what you're talking about? Oh, I'm sorry. Yeah, if you had just aluminum by itself, it would be an element. Yeah. And it wouldn't be a molecule because it doesn't come together unless you had multiple of those guys together. But you would classify it as an element, and it would be referred to as monoatomic, which basically means it just comes as one. Other questions? Yeah, so let me see if I get the next page. I get something better to scribble on here, maybe. There you go. So here's a compound, and that's what we were talking about here. A compound does need to be made up of two or more elements. So let's take a look at sort of the differences here. If we have something like H2, which is basically two hydrogen atoms together, this meets the definition of an element because all of the atoms are the same element. Obviously, there's no other element involved. It also meets the basic definition of a molecule because in this case, there's two or more atoms together. And that's basically a molecule is, it's just a basic definition of you need at least two or more atoms together. It could be two the same, two different or more, but you need at least two to become a molecule. This would not be a compound because it is only hydrogen, no other element involved. When we look at something like water, which looks like this, I'll just kind of draw it like this for now. It is three atoms together, which means it also meets the basic definition of a molecule because it's two or more atoms together. It also meets the definition of a compound because it's two or more atoms of different elements together. It does not meet the definition of an element because it has two different elements involved. Now, something like a compound can be broken down into elements by chemical means. So as I talked about a second ago, you could take something like water, you could run an electrical current over it, you could generate hydrogen gas and oxygen gas, and we'll do it in an experiment down the road with a simple 9-volt battery. We'll break apart water into hydrogen gas and oxygen gas. But once you get to elements, that's basically as far back as you can go. You can't obviously go any further than that, but compounds can be broken down into elements. It does require a chemical change or a chemical reaction basically to do that. Now, the properties of compounds are usually very, very different than the properties of the individual elements that make it up. So for example, let's just talk about an ionic compound, something like sodium chloride, like salt. Sodium is sodium metal, which is a very soft gray silver type metal. And chlorine is Cl2, which is a toxic poison green gas. Through the miracle of chemistry, when they come together, they make salt, right? Which obviously has very different properties. We probably wouldn't want to put, sodium metal by itself on our fries or chlorine gas on our fries by itself. But, when they do come together, the compound itself has very different, I'm assuming nobody wants to do that. It has very different properties than obviously the elements that make up. Same thing with hydrogen gas and oxygen gas to make up water. Water itself, liquid water, has very different properties than hydrogen gas by itself or oxygen gas by itself as well. Any questions on that there? All right, so let's talk a little bit about mixtures and pure substances. A substance is a form of matter that has a definite constant composition. Example, water, ammonia, sugar. A pure substance is something that it's just one thing by itself. And so, for example, if I had water, that is a pure substance. If I had sodium chloride, which is salt, all by itself, that is a pure substance. If I take more than one substance, two or more substances, and put them together. If I did that in that case, I would make something like salt water. That is known as a mixture. So a mixture is when we take two or more pure substances and mix them together. The important part about a mixture is this: even though you mix them together, even though you look at them and go, I can't see any one part of it, might not be able to, everybody still maintains their identity. Nobody changes what they are. And you could actually of a mixture by some type of physical means. That means, technically speaking, when we make a mixture, it is a physical change that's occurring because you can basically retrieve all the parts of the mixture if you do some physical sort of attribute, which is what we're going to do in lab today. Gonna retrieve some of the stuff here. So let's talk about the two different types of mixtures here. Mixtures can be a homogeneous mixture. A homogeneous mixture is a mixture where after sufficient mixing, everything looks the same throughout. So if I took the salt and I took some water and I mixed it together, if I just looked at like the beaker, it will just look like water, right? I won't be able to see the salt. The salt would have dissolved. Like if you took some water out of the ocean, got just water, nothing else floating in the ocean, you know, it would just look like water. But there is salt that's dissolved in there, but it just looks like one sort of layer, one sort of component. Everything mixes really well. That is a homogeneous mixture. Different than that is the other type of mixture, which is what is known as a heterogeneous mixture. A heterogeneous mixture is a mixture that no matter how much mixing you do, you will still see different layers, different components, no matter how much you mix. For example, if I took water and I took sand, like we're going to do today, I think, water and sand and mixed it as much as I wanted to, I can mix it all day. Will the sand ever dissolve in the water? It won't. It will still be there. You'll still be able to see the sand. Just like if you took some metal and sand together and kind of mixed them, you'll still be able to see the metal. Those are what are referred to as heterogeneous mixtures, where you still see different layers. They don't really all kind of come together really nicely and stuff like that. So a mixture can be homogeneous, where everything mixes together, everything looks like one layer. It could be heterogeneous, where you could do as much mixing as you want. It's not going to mix together. You'll still see different layers, or phases is sometimes referred to, like chocolate chip cookies, right? You know, you can see everything going on in there. It's a mixture of chocolate chips, right? And all the other stuff that's there. But regardless, you know, like I said, regardless of the type of mixture, be it a homogeneous mixture or a heterogeneous mixture, you can separate them out back into their original components. So if we look at, say, our salt, our sand and water. So if we took a thing, I'll draw this, sand and water, right? That is a heterogeneous. I guess my sand would be on the bottom. I'll just draw it like that. So we got some sand and water. That's a heterogeneous mixture. We could separate this out by a very simple physical process, which we're going to do today as well, where we could take a funnel. We can put some filter paper in the funnel. And if I pour this into here, what's going to get trapped on the filter paper? Yeah, the sand will get trapped up here. The liquid water part will go through. And by this very, very simple process of filtration, I was able to separate out the sand, which I could let dry, and it's back to its original shape. I could take the liquid water, obviously, which is its original shape, and I now have both of those components together. You could also do something like, for example, if you took some salt water. So if I had some salt water here, that is a homogeneous mixture. And spell very bad. There you go, genius. If I take that salt water, for example, and I just do a process like this and make like a closed container, and there's like a tube that connects the two parts, and I keep that really, really cold. And I put my salt water over here. And I start to heat it with my wonderful Bunsen burner there. As I start to heat the salt water, what happens to the water part? Water part starts to evaporate, which means it becomes steam, right? Which is the gas phase of water. Steam has nowhere to go but through this really cold pipe. What happens is steam, which is gas, when it gets really cold, it then goes through condensation. And now becomes liquid water again on this side, right? So we got our nice liquid water this way. If I continue to heat this salt water, eventually all the water will evaporate off and we will be left with just the salt on this side. So we have our salt back in its original form. We have our water back in its original form. This is a process known as distillation. And it's a really good way to separate out something like a homogeneous mixture where we're taking advantage really of boiling point differences, physical differences, boiling point physical property, taking advantage that the water will boil off. The salt has this tremendously super high boiling point that will never boil. And by doing that, we're able to get rid of the water and separate it out from the salt, leaving the salt okay. And now we are able to change this homogeneous mixture where we looked at it and all just looked like water, nothing different. And now we're able to get back both of our guys in their original. Any questions on that? And that is essentially what we're doing today, except not than that. You're just going to evaporate off the water into the environment, and you're going to get your salt back in your evaporating dish. So, any questions on that? All right, so off